the title of this talk is work stealing for fun and profit, making Redis do things you thought it couldn't do. It's kind of a cheeky title, but I think you'll understand when we're done here what I'm talking about. This is a technique that I was exposed to a couple years ago, and we're starting to use it more and more at the Internet Archive. And it's something I just wanted to share. It dovetails really nicely with Redis, and it's turned into a neat little tool for the tool chest. So just to introduce me, I'm Jim Nelson. I'm a cluster operations engineer at the Internet Archive. The Internet Archive, if you've not heard of us, we are a nonprofit founded in 1996. We're based here in San Francisco. We are an archive of digital and physical media. The original goal of the Internet Archive was exactly that, to make a backup of the Internet. Since then, the Internet Archive has branched out to archiving books, music, film, old software. We have one of the largest collections, probably the largest collection of old retro gaming that you can play right in your browser. And on top of the fact that we have the Wayback Machine, which is 20 plus years of web pages stored and available for playback. We have 1 million visitors per day. I didn't write that correctly. We have 1 million unique visitors per day. 22 years of web archive replay. 300 billion pages are stored in the Wayback Machine. 30 plus million media items total. That's 45 petabytes of unique data. We have our own bespoke archive-centric computing cluster that's located both here in San Francisco and across the bay in Richmond. We are not operating out of someone else's data center. We have our own data center, which is both freeing and exhilarating and scary at the same time. We use Redis at the Internet Archive quite a bit. We love Redis. It's a major part of our operation. We have a metadata directory service that's backed by a 10-node sharded Redis cluster. That's the primary library that I develop, and that's how I got exposed to this concept of work stealing that I'm about to talk about. That 10-node sharded Redis cluster is sort of a general purpose cluster for all of our data needs. It also doubles as an object cache for storing things like database query results, page paints, etc. For ephemeral caching, that's something we may be breaking out in the near future, putting caching in one place and the directory service records in another. But for now, it's all commingled. The sharding is performed by client-side consistent hashing. Most of our code, almost all of our code in the petabox, it's the name of our bespoke structure rather, is PHP, and we use Redis as our client. Each node in our sharded service is supported by 2 replicated mirrors that act as failovers. We also have specialized Redis throughout our services, including the Wayback Machine uses it. Our metadata and full text search have Redis as caching and so forth. We also use it for administrative and client usage tracking and that sort of thing. So before we get started, I've discovered, this is probably my 4th Redis conference I've been to, and I've discovered that you meet sort of everybody here. You get a really neat cross of individuals, some who are first being exposed to Redis, others who have been using it for 5, even 10 years. This isn't a tutorial per se. I'm assuming that you've already written some Redis client code, and that while you don't need to know the exact details of the Redis protocol and the command structure, you should have some knowledge of how Redis works. You should know that Redis is single-threaded, and that's how a lot of its atomic guarantees are offered. You should know that unlike Memcache, Redis offers many different data types, such as strings, hash maps, sorted sets, etc. Basic commands you should be familiar with: git, set, hget, hset. And you should know about transactions. You don't need to know about everything about transactions, but transactions are an important part about what I'm going to be talking about today. And if you don't, these are pretty simple concepts, and the Redis website has pretty good documentation, actually very good documentation on all of these things. So this is how the talk came about. In the past few years, there are some things that I wish Redis could do that it can't do. And the question was, how can I make Redis do these things? One of those things is expire keys only after their time to live passes. Now, this is something that was a hard lesson for us to learn. Our 10-node cluster, while there's a lot of RAM involved, a lot of CPUs, it's constantly thrashing. We fill it up with cached and ephemeral data constantly. And in order for Redis to operate without returning an error saying, I can't take anymore, Redis, when it's under memory pressure, will automatically evict keys in order to free memory for new keys coming in. The problem is that it will evict keys even if their time to live hasn't expired. So if you mark something as expiring in 1 hour, say, it could expire in 1 minute. For a lot of caching needs, that's perfectly acceptable. But for some things, it's not. The trick here to understand is if you mark a key with the expire command, that sets the key as volatile. And if it's volatile, it is up for eviction. It's sort of like it's putting a death sentence on that key. It can at any time be evicted. It really depends on a number of things. It depends on how Redis is configured. Redis has an LRU policy as well as you can configure it for an LFU, least frequently used policy. And that may change how the eviction occurs, what circumstances that happens. But at the end of the day, if the Redis server is out of memory and a new key comes in or more writes come in that require more memory, what Redis does today, and that may change in the future, is it will randomly sample a configurable number of keys, 6, 8, 10, and the one that is the least recently used or the least frequently used, depending on the configuration, gets the axe. And if that frees up enough memory to write, great. And if it doesn't, it does another sample. So what that means is that ephemeral caching generally works. That means that whatever was cached is now evicted, and you're going to have a cache miss the next time you read from it, and you have to recompute that value. But there are some situations where you absolutely really want that key to stick around for the amount of time that you've entered. I'm thinking of like distributed locks, items or values that are expensive to recompute, like long database queries or something that requires a lot of churning CPU to produce. If you have to lease something, you're leasing software, you're leasing a network resource for a hard amount of time, 1 hour, 2 hours, you really don't want that value pulled from Redis before the time to live is expired. And so I kind of always have wished that I could sort of flag a key and say, you know, this is a hard time to live. You need to not evict this just because you're out of memory. You really need to hold on to this. But when that time to live is reached, go ahead and evict it and free that memory. Unfortunately, that doesn't exist currently in Redis. The reason for this, as I've mentioned, our Redis cluster is constantly under memory pressure. We have a monitor that tracks key evictions. Under heavy load, we'll see up to 1,000 keys per minute being evicted. The way that I would scale this, you might have remembered earlier, I had said that we have 30+ million media items. That means we have 30+ million content identifiers. Those are the kind of things, that wind up as keys in our Redis database. And because of that, we can't store all of that information in Redis all at once. There's simply no way around this. We're going to be always thrashing under memory pressure. So all of their metadata is competing for precious bytes. As I mentioned, distributed locks, leases or licenses, expensive recomputes. For these, we need deterministic expiration. And for the other keys, the ephemeral data, we're happy to allow Redis to evict them as necessary to make room for more frequently used values. There's something else I wish I could do with Redis. in Redis, only keys can be set to expire. But I've had a couple of applications where I want to have a hash map, key value pairs, and I want to be able to individually expire the values in that hash map. I'll be showing an example of that in a minute. Unfortunately, there's no real way to do that in a automated way with Redis as it stands. For example, I might have a hash map look something like this. We have a field, content ID with a value, and I'm going to set the time to live for that to just, as an example, 12 hours. And then another field is the number of likes that that content has, and I want to expire that for 5 minutes. And then we keep, for example, a list of other items that are related to this particular piece of content, and I might want to expire that in 1 hour. In other words, I want to have a hash map where each individual field expires, but that the entire, all this data, which is correlated, is stored under a single key. So, these are just a couple examples of things that I've been wanting to be able to do with Redis. So one approach is this approach: cron jobs, daemons, schedulers, etc. In other words, you write automated background tasks to monitor Redis. You have a script that's fired off once an hour or once a day, or a continuous polling daemon, or a program that's in a hard loop that is constantly monitoring Redis and going through and garbage collecting anything that needs to be expired. However, there's some limitations to that. For one, cron jobs may fail to run, or worse, we've seen this at the Internet Archive, where an improperly written cron job, there was actually multiple instances of it running at the same time, sort of stepping on each other. Daemons can be tricky to write. And all this creates a single point of failure, and there's usually a lack of failover. It all comes down to allocating dedicated hardware to run background jobs. There's this notion you've probably heard before of pets and cattle. The idea is that in your data cluster, the cattle are named like IA600413 because you've got hundreds, maybe even thousands of machines that are all near identical copies, all running similar software but have their own data stores. And then the pets are machines that are one-offs, and they're usually named like DB1 or Redis 0. Those machines are sort of like the ones that you worry about at night, because if they go down, that means vital systems go down, maybe even the whole entire website goes down. The point is that when we start talking about cron jobs, daemon, background jobs, to facilitate this sort of garbage collection and monitoring of Redis, you're talking about putting that code on a pet. And if you've ever had a machine go down on the weekend, one of these pets, and your cleanup tasks stop running, then you know exactly what I'm talking about. Suddenly things back up, suddenly Redis fills up, memory is not free, etc. That's what I didn't want to do. I didn't want to have to dedicate code to run on a particular machine. And that's where I came up, I started using this strategy. And the phrase for this is called work stealing. I should first of all point out, I didn't come up with this. I want to make sure it's clear. This isn't my idea. I didn't invent this. What's more, the term work stealing is actually borrowed from the multi-processor, multi-threaded computing. The way I was exposed to it, funny enough, is by a guy right here named Michael McCabe. He used to work at the Internet Archive. He actually worked on the piece of software that I've inherited. And he was using it to solve actually a problem I'm going to talk about in a bit. And when I saw how this was working for this one particular instance, I generalized it so we could use it for other things within our computing center. So I just want to make sure I'm going to get that out of the way first. So what is work stealing? It's a funny phrase. Matter of fact, one of the ushers was saying, I don't know what the next talk is about. It's something about stealing work. This is the basic idea. You have pools of workers in your computing center. The idea is to steal spare cycles from those worker pools. Sometimes I've seen this in some of the literature is described as mugging or recruiting workers. They go off to do their primary task, and then you sort of redirect their processing power to perform a little small slice of work on some other task. Once they finish that small slice of work, they just move on. They're done. And if they're unable to finish the work, this is important. If they're unable to finish work, you don't sweat it, because the next recruit will pick up where the current one left off. You don't do retries. You don't have to worry about network failures. You don't have to worry about retry logic. If this one doesn't finish it, the next worker will finish it. And it actually winds up creating a situation where the code is much cleaner than if you had tried to write all this code in a single class that has to sort of deal with both adding data to Redis and cleaning up data that needs to be garbage collected at the same time. And that's it. The whole idea of work stealing is really simple, and it actually turns out to be quite powerful. I've been able to use it in a lot of different situations, and it turns out that it works really well with Redis, and that's why I'm here today. So where do you find these workers? Where do you find spare cycles to steal to perform some of this extra background work? Well, web server pools are a good place to look. Or if you have a task or priority queue where workers are spinning, pulling things off of a queue and processing work. Thinking of Kafka, for example. Any place where you're doing cache fetches, and if there's a cache hit, you view a cache hit as that worker has been saved a lot of work. They didn't have to go off to the database. They didn't have to go off the disk. They just pulled what they needed off the cache. So that worker can probably be spared to do a little extra side work as well. So in general, for finding workers, look for anywhere in your system where you've got a pool or group of workers constantly servicing requests, and anywhere where the worker code may have what you call like a fast exit, such as a cache hit or a no-op, or like there's little or no work to be done. That's a good place to then grab that worker and redirect them to do some work stealing. So as how we do it is we still work from our content directory service. That is, all the content, that's 30 million items, we have a lookup service that returns JSON records for all of them, their location, the content that they hold, metadata, etc. That directory service is constantly accessed by our web servers. So, and it's stored in Redis. It's essentially Redis acts as a record cache. So if there's a cache hit, that worker during a page paint, becomes a candidate for recruiting. We only need to recruit 0.3% of the total work pool to get all of our background work done, and with workers to spare. And the reason I know that is because we've instrumented all of this, and so we know how many of those workers are being redirected, how many of them are actually doing work, and how many of them don't have work to perform. I'm going to talk about that in a little bit too. The point is that when I say workers to spare, what I mean is it's an order of magnitude. We're actually recruiting 10 times more workers than we really need to get the work done. The reason that's okay is that if there's ever an outage or for some reason our web traffic dips, we still have, that's like slack space. That's spare cycles to make sure that all that garbage collection is still happening, even though, for example, the website, the amount of traffic drops by a factor of 10. So let me go back to one of the examples that I talked about earlier, things that I wish I could do with Redis, but I couldn't do normally. I talked about having a hash map where each individual field can expire. So here's how I might implement that. So to store a value, I store in the Redis hash map the field and its value. That's pretty straightforward. That's a pretty standard Redis operation. In addition, there's a sorted set that exists alongside the Redis hash map. And in it, I store the field name for that hash and an expiration time. So here's how it would look in code. We start a transaction using the multi-keyword. We set the hash field with an H set, and that first value, the hash :user:1, is the hash key, the key for the hash map. The field name, the value, and then using zadd, which stores it into the sorted set, the time t, which is the expiration, and the field name, and then an exec, which commits that data to Redis. It's pretty straightforward. So then to read a value out of this hash map, 2 operations. Read the value from the hash map, and then read the expiration time from the sorted set. That expiration time, if it indicates the field has expired, we simply return to the caller null or undefined or whatever your language uses to indicate that the value doesn't exist. And again, it's pretty simple. We start a transaction, get the hash field using hget. Hash user1 is the key name, field name. The field's expiration time is stored as the score in a sorted set. zset user1 is the sorted sets key, and that's the field name. The expiration comes back as the score, and then we commit the transaction. But you'll notice between those 2 operations, there's no garbage collection. If one of those fields has expired, it's not being deleted. So under normal operation, these hash maps could potentially grow without bounds and fill up all the space, free space in Redis. The initial thought that I had when I was sort of going down this path was, well, eventually, the next time the user requests that piece of content, we can take that as an opportunity to do cleanup. But the problem is when you've got 30 million content identifiers, it's possible that a user will request information from a piece of content and then no one looks at it again for a year. In which case, you've got that piece of data just floating in Redis for a year, waiting for another worker to come through and access it to clean up those expired fields. What I needed was a background job that would clean it up. So this is sort of like a logical idea of what this data structure looks like. Even though it's actually 2 separate structures in Redis, logically, to the caller, it looks something like this. So how do we expire those fields in the background constantly? Well, a worker is recruited from the web pool when there's a cache hit. If the recruit randomly selects a single hash map, and notice of all those content ideas, that's actually being stored in a separate list. It reads the sorted set to determine which fields have expired, and then simply deletes from the hash map those fields. So work stealing allows for garbage collection to occur in the background without creating specialized scripts or bots. And this is what that looks like. This is the work stealing. A worker's been recruited. We put a watch on both the keys, the hash map and the sorted set, before we start. I'll get back to what that does if you're not familiar with the watch command. The first thing it does is it uses the zrange by score command. It's a sort of an odd looking command, but the negative infinity and the time, that's time t, the local time, limit 5. What that means is give me the 5 oldest fields in the hash map. Only 5. If there's no fields that have expired, then we're done. We exit. The background worker has done its job and can move on. But if there are fields to expire, it starts a transaction, it deletes those fields, it removes the expired fields from the sorted set, and then it commits the transaction. This is the garbage collection right here. So what is that watch doing? If you're not familiar, watch is it's an unusual way to perform optimistic locking on keys within Redis. Basically, when that watch happens at the top of the screen, that puts your Redis connection to a certain state. It indicates to the server, from this point on, if these keys are written to, then I want you to abort the next transaction if it involves any of those keys. And that's really key here. That wasn't a pun. That's really important here. What it means is that If the hash map or the sorted set is touched after we read that list, then the exec at the bottom of the screen will abort and no changes will occur. That means that if another writer from the outside, another computer on the cluster, makes a change to this hash map, the background garbage collector just aborts and it just moves on. It doesn't retry. That's important. I'll come back to this in a bit. It doesn't retry. It made an attempt. It made a fair attempt to get those values garbage collected. It just aborts and moves on. The thinking being that another garbage collector will come along and take care of that in the next round. So, to expand on that, any failure outlying condition is ignored. If the hash map is empty, we just exit. If no fields have expired, we just exit. If there's a failure to connect to the server or a network error, if the watch triggers an abort, or if in this example we don't use one, but you could imagine using a distributed lock to guard access to certain Redis data structures. If you fail to acquire a distributed lock, you simply exit. Because you're sort of stealing these slivers of spare cycles from the workers, if one of them fails, the next one will pick up where they left off and take care of the job. The other thing to notice is that only a small amount of work was being done. That limit 0.5, that indicates we only want 5 of those values from the hash map. The hash map, for example, could have 2,000 fields. We're only asking for the oldest 5 ones, the oldest five fields that may have expired. That limits the amount of work that the background worker is performing. It doesn't have to delete a lot of things at one time. The idea is that having a large number of workers performing this work means that each only has to perform a small amount of work and that a lot is being done in aggregate. And the example that I sort of like to compare this to is the children's story Stone Soup. The idea is that a couple of men enter a village and they hook up a pot of water and put some stones in it, some rocks in it, and say, we're making soup. And all the villagers come by and say, what are you making? Well, we're gonna make some soup. It would be great if there was some carrots. So one villager adds some carrots and another villager says, well, maybe it'd be good with some potatoes. So the next villager puts in some potatoes. And pretty soon all the villagers add just a little bit, little salt, little pepper, all the various ingredients. And before you know it, there's this entire rich soup that the entire village gets to consume because everyone contributed a little work. No one had to put in all the effort. And that's the basic idea here. So here's another example. I'm gonna check my time here. Okay, great. Another example. We have a custom task queuing system that performs all of our content transformations and mutations with any analysis or derivatives that we want to produce of the content that's uploaded in the Internet Archive. We have certain subsystems that need to know quickly if a particular content object has work queued or is running. It's because that means that the item is changing, and that may involve updating state in another system. The important thing to know here is that even though we have 30 million pieces of content, only a tiny fraction of them, a small percentage of them, are being worked on at any one time. Most of them quiesce. Usually something gets uploaded, it gets transformed and mutated, and then it just kind of settles down and goes into sort of a read-only mode. So in order to track when a content identifier has queued tasks, we have 2 work-stealing jobs. The first is walking our database, which is the task queue in our system. And as it walks the database, it pulls those content identifiers out of the rows and it adds them to the Redis table. And again, here, the Redis worker is only responsible for adding a small number of tasks, like 50 rows at most. It's not reading the entire table, just tiny small slices of it. It adds those content identifiers, and then it stores the row ID in Redis so the next worker can pick up where they left off. So then the other work stealing job removes content identifiers when they no longer have work queued. So when all the tasks have completed, we want to remove that content identifier from the Redis table. The way that works is by randomly sampling from that table in Redis, just picking 5 values at random, and then querying the database to see if those content identifiers still have work queued. It turns out that works really well. With the number of workers that we can peel away from our web pool, that could actually clean up that list quite efficiently. Within just a couple seconds of a piece of content going quiet, it's removed from the list. And here's some sample code. Again, you'll see watch at the top. This is the task queue follower. It uses srand member, excuse me, to pull from the tasks queued set five identifiers at random. And then I'm not going to list out the database query. It's just SQL that asks, of these content identifiers, which ones are still listed in the database? If they all still have tasks queued, then it just exits. It moves on. There's nothing to remove. If there are values in Redis that no longer have work queued, we start a transaction, use srem, which will remove those quiesced content identifiers from the set, and then we exec, and that's it. I mean, it's the reason I've been so excited about this is that the code has become much, much cleaner. Being able to, for the readers and the writers of these data sets, they don't have to worry about any cleanup. They can just simply read and write the values that they want and let the background task workers clean up any garbage that may collect. And if they have errors, they simply exit knowing that the next worker will take care of it. It's actually, I can't emphasize how much this has cleaned up the code, made my life a lot easier. So in general, what I would suggest if you go down this road, when you think about how to write these work stealing routines to do this kind of garbage collection or monitoring or tracking, watch is important. And I would really recommend going to the Redis website and studying how watch operates. It's very important for this operation. Otherwise, you'll wind up with race conditions and other nasty, hard to track down bugs. Random sampling is your friend. What that means is because you're sort of throwing all of these extra spare cycles all at once at Redis, you don't have to mechanically or naively iterate through every value in a list. You can simply pluck a random sampling of them and then check to see if they should still remain, if they should be evicted or not. If you have failures or there's outlying conditions, log them, add them to statsd, Prometheus, keep track of them, but don't retry. Don't retry network errors. Don't retry locks, unable to acquire a distributed lock, for example. Just let the next worker make the attempt. Because each recruited worker is only performing a small slice of work. And it's not vital that any one worker finish its job completely. Another worker will come along and take care of it. So as I said, to come back to this, I'm not saying throw every worker that you have at this extra work. The approach that I like and has worked well for us, this is what I picked up from Mike McCabe. When workers are enlisted, if they fast exit in a particular bit of work, if there's a cache hit, if they paint a simple web page, if they don't need to query a database or the database comes back, the database query comes back with an empty result set. Have each of your work stealing jobs declare a rate, a percentage of enlisted workers it needs to do its work. For example, we just use plain floats, 0.001 to receive 0.1% of the enlisted workers. And if you have more traffic, use a lower job rate. These are just static numbers. This is a really simple approach. And then every time a worker is recruited, every time a worker performs a cache hit and it comes in to do a little extra work, it generates a random number. And if it's under that job's recruiting rate, it will then do the work. And if it's not, it's dismissed. It doesn't have any more work to do. And here's just some pseudocode to explain how this works. Imagine having like a class that holds a list of all the jobs that need to be done in the background. Each one has a rate. And list is called from after a cache hit or some other fast exit place in your code. Random numbers generated, and then each job is iterated through, and if the random number meets that particular job's rate, it goes off and does that work, a tiny little slice of work, and then it exits. It looks simple, it's deceptively simple, it works surprisingly well. If you notice, there's no extra state. We're not tracking the number of workers, we're not using distributed locks, there's no job queues. It's just a random number that decides whether or not a worker is going off to do this extra work. And we're doing this in production right now, and it's working great. The only thing the caveat I would ask is instrument your code, use statsd, Prometheus, etc. You want to know how many workers are selected for background work, how many finish their work, how many stop for errors or aborts. And then as you track your values, you can then fine tune your job rates so enough workers are being recruited with some padding. And I have up on GitHub a really simple framework with some sample code that takes some of these concepts that I've got in PHP and demonstrates how to work them. I would call this a start for your own use. I wouldn't build an empire on top of it. But the idea is you should add logging, stats gathering, error checking, and so forth. And we have about 8 minutes left if anybody wants to ask any questions.
Quick tangent. Did you do xfetch once?
I did, yeah. 2 years ago, I did a talk on early probabilistic recompute called xfetch. Yes.
I really like that one too. Really like your talk here too.
Oh, thank you.
Do you have? I actually missed the beginning. Do you have the slides up somewhere? I had a question about this work stealing job part.
Sure. You know what? What I'll do after probably the next couple of days is I'll post these slides in the GitHub repo. Thank you. And along with the sample code.
Okay. Yeah. The synopsis says something about adding tiny bits of work when your queues are idle. If they're never idle, you just aggressively throw one thing for them to do occasionally or something.
That that is something you could look at. I mean, realistically speaking, you could throw all your workers to do this small slices of background work. It really just depends how responsive you need, how much work you need to be done. I like this approach of looking for these fast exits, cache hits, that kind of thing, for obvious reasons.
Yeah. All right. Thanks.
Sure. Oh, right up here.
Is there anything you don't recommend this for and would leave in cron jobs or whatever?
I mean, I wouldn't do this for absolutely mission critical type stuff. This is using sampling. This is using random numbers. It's not exactly the most deterministic thing, but like I said, I think for monitoring, garbage collection, auditing, it works surprisingly well. I think like most technologies, it's sort of like it takes a little taste and knowing what works in what situations and maybe where it's not ideal. That might be it. I'll be up here for a couple minutes if anyone wants to ask me questions up here. Thank you very much. I appreciate your patience.